Hey, how's it going? We're about to do Kickstart Round F, and here we go. Alright, let's start with the first problem. Color, durability, unique identifier. Okay. Okay, so make a struct for the fabric, string C. Sure, let's do that. And then we're gonna sort first by probably shouldn't have capitalized it. Then, okay, cool. We'll just do this. And then so YD and then YU. All right. Cool, that looks good. We'll pick plus and submit. All right, problem B. All right, we got it. I mean, it doesn't really matter how it's connected, it just matters how many levels there are. So okay, so yeah, we're just trying to count the levels. This is kind of overkill, but I'm just gonna paste in my tree template. right. I see. Okay, so all right. You don't care what that is. Yeah, and now we're just gonna go by depth. This is B. Sorry, which one did I paste in? I pasted this one, 1 and 1, 4 and 1. All right. Let's do it. Next problem. 3 parts, okay. Quantity. All right, so in second. Seems like it might not be that easy. The most X seeds per day. QI, this one. Okay, huh? Okay. Okay. Oh, interesting. Okay, so Yeah, okay, I think I know the general idea here. Oh, D is not very big. Okay, so yeah, you just sweep, and you have these blocks. You just unlock positions, and you're trying to track the sum of the top, or the smallest K as you go. Yeah, so modifications. Okay, as you go. Um, you can do this with a display tree, you can do this with a heap. A couple ways to do this. I think I'll go ahead. I think I'll just do it with the display tree. This is no, it's not what I want. Okay, so just get rid of that, and now to no, we don't need a map. Yeah, we do want this. Yeah, I think we're good. I think that handles it. And now, okay. Can also do the heap approach, but this seems fine. Right, so we read an M, and then we have M meetings. So oh wait, no. What's the condition? If L is less than X, then you are in the meeting. Yes. Yes. Okay, so now we have increase events and decrease events. The increase event occurs when increase events yeah. Yes. Decrease events. Yes. Okay. Oh, so I can do that. Cool. Now, uh, yeah, and then oh, I see. This is D, right? This is D. We're gonna run it. All right, I think we're good. How do you feel about this? So, yes, yes. X is always at most D. Yep. All right, and now to C. So this is a tricky one. So we need to. Okay, so we don't need to. We don't need to worry about when we make money. We just do this whenever. This is your main constraint. X seeds per day. Nice. All right. All right. And first, right now. So what we need to do. How much is TBT? That's a lot. At most X per day. I think you just go through the days in reverse and just create. D and X. QI, LI, VI. LI is at most D. L is big. Q and V are small. Okay. I think we want to sort them by L. Excuse me. All right. Oh, but DB can be huge. So what do we really want to do? They're just sections based on L. You just fill those sections greedily. So you want the maximum value. This is just so. Right, so we're going to do that, and then we're going to. Okay. Yes, so we know how many slots we have. Slots is going to be aftermost times X. While slots are 0 and not empty, we're going to take. We're going to take the top. Top. think that's it. 13, no. Interesting. 2, 3. Why don't we have a 4? Is this what we want? Okay, I think this is what we want. Let's do it. Oh, got there just before me. Well, it's about 2 minutes. This is fine actually because, yeah, we do have that last one day. It should just be D. This is not possible, so we don't have to worry about that. Oops. All right, we got it. Cool. Second place finish. We'll be right back to talk about the ideas here. All right, so the contest is a little over halfway through, and a lot of people have managed to get the full 100 points by now. So anyway, let's jump in. Let's talk about these problems. So first we have problem A, sort the fabrics. This one is definitely the simplest one. They basically describe to you a process where two people are sorting the fabrics in two different orders. and then you want to know how many of the fabrics end up in the same position between the two orders. So you pretty much just do what is described in the problem, and you what I did is I made two arrays of fabrics, sorted the first one the first way, first by C and then ties broken by U, and then made a second array, sorted that the second way, sorted by first by D and then ties broken by U. And then you want to know how many are the same, and then because you have this unique identifier, that becomes pretty easy. You can just check how many of the U's match up, and then you just output that. So this one, fairly straightforward, is just an implementation problem. And also you can kind of speed things up by noticing that U is unique, and you can use that as an identifier. If it weren't for that, you would have to add the index to the struct or class, and then use that to compare whether two things were equal. But because you have this, it's nice. Cool. Problem B. So this problem is about a tree where each node can hold some amount of water. And we're given a bunch of, they call them queries. They're not really queries because you only have to output one thing. You only have to find one answer. You don't have to find something per query. But basically, at each point, we add 1 liter of water to a particular container. And then if you kind of dig into what's going on, you have a tree, right? It's sort of an upside down tree because the root is at the bottom. Then every time you add water, the key thing to realize is that it doesn't matter where you add water, because here at this point, if I add water, whether I add it to 2, 3, 4, or 1, it will fall basically down to 1 until it comes back up and kind of fills 2 and 3 halfway. So we'll get to this point regardless of where we're adding water next. And then basically they want to figure out how many of the containers are fully filled by the end. And so this ends up being also pretty simple. I used my entire tree template, which is called LCA, even though I really didn't need it. I only needed depth. That's the only thing that I used. But it's just convenient because then I can just call this instead of having to, otherwise I would have to write a DFS, which is not bad, but this just kind of saves me maybe a minute. So I did that, build a tree. This is kind of a funny part. You just read all of the queries and you throw them away because it doesn't matter what they are. Now we're counting how many nodes are at each depth. So it's kind of like the size of each level. In this case, the bottom level is 1, the middle level is 2, and the top layer is 1. Yeah, and then while we have, basically Q is the number of liters of water we put in. So while we can fully fill the level, we fill that level and go up to the next one. Once we hit a level that we cannot fully fill, we do not include that at all. So in this case, the answer would be 1 because 2 and 3, even though they're half filled, they're not fully filled, so we can't include that. Yeah, so then we just have a simple loop while there are more levels and we can fully fill the level, just add that up and then print the answer. So yeah, also a relatively simple one once you figure out what's going on here. All right, problem C. So this problem involves a farmer planting seeds and growing vegetables. You have n types of seeds. For each seed, you know how many you have, how many days it needs to mature, and then once it does mature, how much money you can sell it for. And your main constraint is that you can plant at most X seeds per day. So essentially, you're just trying to plan out your planting in a way that by the time D days are finished, you've made the most amount of money possible. And N can be quite big. N can be up to 10 to the 5th, so 100,000. D is even bigger, 10 to the 12th. X also quite big. And then Q is up to 10 to the 6th, same as the values, 10 to the 6th, and so on. And so this type of problem, often you want to make observations, make kind of greedy observations and then show why they're true. In this case, there's really one key greedy observation, which is if we think about the days that we have, we know that we have X each day. So for example, on the first day, what should we plant? It's not super clear because we could obviously we won't plant anything that will not finish, but it's possible, we could plant something that finishes sooner that could make a certain amount of money, or plant something that finishes later that makes a certain amount of money. And basically, it turns out that if you go from beginning to end and think about what you want to plant, it's tricky because it's not clear whether you should plant something that finishes sooner but makes less money, or something that finishes later but makes more money. Because in that case, maybe you want to save the thing that's sooner for later, and maybe you don't want to save it. But if you go backwards, so if you go from the end to the beginning, then now what you have is a situation where you have a certain number of seeds that can make it. Everything that cannot make it, you're not even considering. And if you're going from right to left. So basically anything that can currently make it will always be able to make it later on, because we're going even earlier after that. So we can just kind of greedily pick out of the options that we have, just pick the ones that sell for the most. And that's the key idea here. So we go through the days from end to beginning, and then as we do, we put things into a heap, a max heap for what sells for the most, and we just repeatedly grab the thing that sells for the most. The problem here is D is too big. We can't just iterate through all D days. So instead what we do is we can iterate through the values of L. So this is a little tricky, but basically by going through the values of L in order, then we can kind of find the cutoff points for, oh, here's the first point where this seed would actually work. And so we're just kind of going through in order and doing that. We sort by L, increasing, and we go through. And basically, we're considering the period L days before the end up to the next L days before the end. And that's kind of the number of days that we have in our window. So the number of seed slots we have is that number of days times X. And also don't forget to add to the priority queue. And so we're just grabbing seeds, the most valuable seeds, and filling slots with that until we can't anymore. And that's it. That's the whole idea. So once you see the right order to think about the days, then the greedy becomes pretty straightforward and works. All right, one last problem. It's problem D, scheduling meetings. You have N tech leads that have certain schedules. You know their schedules. You need to find a meeting that lasts, I think it was X hours. And you need at least K of the N tech leads to show up to the meeting. In order to do that, you have to cancel all of their meetings at that window. So if you decide to pick the window 0 to 3 and you need 2 tech leads, you can pick tech lead 1, who's already free, and tech lead 3, in which case you need to cancel meeting 4. And they want you to figure out what is the smallest number of meetings you would have to cancel in order to get K out of N tech leads for X hours. And again, N is going to be pretty big, 10 to the 5th, so we can't do anything quadratic. So here, the real idea is, it's a pretty straightforward sweep. It's like a line sweep. Once you've done a number of problems on sweeping, this is very similar to those. And we're going to go from left to right and just look at all the different X hour intervals. And for each interval, we want to know how many meetings we need to cancel. And so what we do is, in my case, I'm just tracking how many meetings each tech lead has in the window. And I have a series of events. So there are certain events, when you hit a certain time and you're sliding your window to the right, you need to increase your count for a certain tech lead because a new meeting comes in to the window. There's also decrease events where you need to decrease the count for the window because that meeting leaves the window. And so we're just tracking all these events. You need to be careful about off by ones, but otherwise you can handle everything. And then I'm just iterating my window from left to right and trying to keep track of how many meetings each person has. And then the key idea here is in the window. And the key idea here is you need to add up the K smallest meeting counts out of the N tech leads. So how do we do that? There's two ways to do that. The way that I did it is I ended up just using my splay tree. My splay tree already has the ability to query the prefix with a certain number of nodes. and then you can just call get sum here in that case, which does it. Another way you can do it is because you're always querying the same value for k, there's an idea where you use two heaps. One is a max heap for the lower half, and one is a min heap for the upper half. And you kind of push things back and forth to adjust the count so that the lower half has exactly k. Yeah, and then in my case, I'm just kind of maintaining the tree over the events. I'm erasing the old value, and then either incrementing or decrementing, and then inserting the new value into the tree. So that way I always have the correct n values in the tree, and I can just query the k smallest. Yeah, so that's it here. So this one is n log n. I guess in this case plus d because of the way I did the sweeping. If d were really large, you would have to do coordinate compression to handle it, but luckily d was smaller here, so I didn't have to worry about that, and I could just iterate up to d. But yeah, that's Kickstart Round F. Solid finish here, and hopefully you learned something, but feel free to check out my other videos, and I'll see you in the next one.